11.3 in Math 31 introduces the substitution rule, and it's really aptly said right here. To reverse the chain rule, we use the substitution rule. So any function that required the chain rule to take the derivative of would need the substitution rule to take the antiderivative of. And they show the chain rule here. So the derivative of a composite function is the derivative of the outer function times the derivative of the inner function, which means with that integration process, and I'd like to draw it here, that if I take the integral on both sides here, it cancels the Leibniz derivative. And so we get that the integral of capital F prime of g of x times g prime of x is equal to capital F of g of x. Now, I don't really like that notation. It can get, you got to say capital F and g of x and stuff like that. So another way of writing this is if we say instead of g of x, we say a function u. So then what we can say f prime evaluated at some u times the derivative of u, which is the derivative of the inner function, and students usually get a kick out of this, is equal to f of u plus c. Fortunately, there's no k constant there, so we get away with it. So when we look at the bottom one here, it shows that the antiderivative of f of g of x can be written as the antiderivative of f of u du. Now, the challenge is that we have to use a little bit of critical thinking and try to identify what we should make that inner function so we can get away with using this substitution rule. Now, they show it again with the substitution rule, and I'm going to try to keep the notation as consistent with this as possible. Again, with so many other integration techniques, the more you practice this, the better you're going to be at it. And essentially what we're going to do here is we're going to take a function written in terms of x, an integral, sorry, written in terms of x, and we're going to rewrite it as an integral in terms of u. Now, the problem is when you get to the end, what's u? U has no context in the original question other than the way we define it. So we have to back substitute whatever we identified at the beginning to get the original function. But I really want to stress that if you're worried about whether you've done it correctly or not, take the derivative of your final answer and it should get you back to what the question gave you. And that is such an important thing in math that, like so many other concepts, in the last 3 years, you can verify your answer by, a couple different techniques we've taught along the way. So let's look at one right away. And in most situations, whatever, expression is inside of a bracket becomes what we're going to make u. So what I'm going to do is I'm going to identify that the function f evaluated at u is going to be x squared minus 5 to the power of 8. Now, the reason that this is a benefit is now I can say, okay, that u, and this is just a substitution we're making, is going to be equal to the inside of that expression. Now, what this allows me to do is I can rewrite this integral. Instead of x squared minus 5 to the power of 8, it's going to be u to the power of 8. Now, the problem arises if we have multiple variables inside the integral. We don't know which one is the variable and which one is maybe a parameter like the density of metal or specific heat capacity or whatever that is. So what we need to do is once we've identified u, I have to be able to identify what du is. And essentially what we're doing here is we're taking that derivative on both sides, and I get that du, so the derivative of u, is equal to 2x times the derivative of that x. And the Leibniz piece is really important there because it allows us to take this expression and replace it with du. So really importantly, I'm doing two substitutions here. I'm identifying that u in red is going to replace the entire bracket there, or the inside of the bracket. And then I'm identifying that 2x dx is going to get replaced by du. Now, some students will try to make the u x squared minus 5 to the power of 8. And I'd like to show you how south that goes really quickly. That if I made u x squared minus 5 to the power of 8, now du is 8 times x squared minus 5 to the power of 7 times 2x dx. We do not have all of that in our derivative, or in our integral, I should say. So you can make the wrong substitution, but if you don't see, a relatively compact expression that you can substitute, you've probably made the wrong decision. Now, that's okay, because it just means if I tried this technique in red and I saw that it failed, I go back and I try a different substitution. And that does, sometimes introduce a struggle for students. You are not going to get all of these questions the first time. Right? You have to make sure that if you make a substitution and you make the question worse, you go back and you try a different substitution. And I really want to showcase that this integral is very, very difficult, although I guess technically possible if you were really on the ball with the chain rule. The integral that I've replaced it with is, I hope, relatively simple. It's the indefinite integral, of u to the power of 8, which is 1 over 9 u to the power of 9 plus a constant. So that's what my indefinite integral is equal to. And this is the point of these advanced integration techniques, is they should make a very, very complex integral. And I don't want to say easy because it is calculus, but relatively easy, or at least easier than the first integral presented. But again, I want to emphasize this so much that you can't tell me that this is equal to 1 over 9 u to the 9 plus c. What's u? So we have to take the substitution that we made. We said that u is equal to x squared minus 5, which means the u in this expression is going to be 1/9 times x squared minus 5 now to the power of 9 plus a constant. And I really want to emphasize the concept that what we have just finished saying here is that the derivative with respect to x of the value of our integral, so that's 1/9 x squared minus 5 to the power of 9 plus a constant, the derivative of that expression is equal to the integrand, the expression inside the integral, which is x squared minus 5 to the power of 8. And then I'm going to write that 2x dx just to make sure you remember that we are taking the derivative with respect to x. Now, I think this is such a good idea, and I really want to push this. Check, at least initially, if you're not sure if you're doing this right, check it, take the derivative. The derivative of 1/9 x squared minus 5 to the power of 9 is 1/9. We're going to take that constant out. I'm going to multiply by the exponent on the bracket, then reduce that exponent by 1, and then multiply by the derivative of the inner piece, and that dx is just included to make sure that we are taking the derivative with respect to x. These cancel, and I get the expression that was inside the integral. Really, really important to push that concept home that we are doing the opposite operation of the derivative. All right, let's try another one here. They immediately get a little bit harder to work with, for sure. But the one thing that I really want to push is that the derivative of x cubed is x squared. So the derivative of what's inside that radical in the denominator is actually present in the question already. And that is really something that, shouts that we have to do substitution. So I am going to make u equal to the inner function, which is 1 minus x cubed. And if u is equal to 1 minus x cubed, then the derivative of u is equal to negative 3 x squared dx. Now, the bummer here is that I don't have negative 3x squared dx. But like any other equation, this is manipulatable. So I'm going to divide both sides by negative 3. I'm going to write this a little weird. I'm going to write it as negative 1/3 times du is equal to x squared dx. And the reason I need to do that is because x squared dx is inside that integral. And I'm going to rewrite it just a little bit. I'm going to rewrite this as the integral of, and I'll write it as 1 over the square root of 1 minus x cubed multiplied by x squared dx. These are the same thing. It's a perfectly acceptable thing to do. But now I'm going to put my substitutions in. So this is going to become the integral of 1 over the square root of u times x squared dx is equal to negative 1/3 times du. And that's a really big benefit because now I can use that constant, multiplier rule, and I can say that this is equal to the constant in front times the integral of, and I'm going to rewrite that u as u to the power of negative 1/2 times du. And the point of this is it should make the integral easier to work with. That takes practice. It takes a lot of effort and a lot of work, but we do want to make sure you get used to how to do this because advanced integration techniques are very important. All right, we can take the integral now, so I'm going to leave that constant negative 1/3 out front. I'm going to multiply by, so I'm going to increase the exponent by 1. I get u to the 1/2, and that's going to be 1 divided by the new exponent, which is 1/2, and then I'm going to add the constant. Now, I wouldn't leave it like that. I'm going to rewrite this. 1 divided by 1/2 is 2. I multiply it by negative 1/3, so I get negative 2/3 u to the power of 1/2 plus a constant. And yet again, this final solution makes no sense based on the initial integral, because what's u? There's no u in that initial integral. So the final step is to substitute it back in. We said that u is equal to 1 minus x cubed, so we're going to substitute that in, and I get, and I'll rewrite it again, that the integral of x squared over the square root of 1 minus x cubed dx is equal to negative 2/3 times 1 minus x cubed to the power of 1/2 plus a constant. Now, I'm not going to do it again on this question, but I would highly encourage you to check your answer if you're unsure. As you're working through the textbook, they do for some reason like the radical symbol. So you will likely see this if you're checking the work in the textbook, but remember that those are the same thing, right? The square root is the exponent 1/2. Okay. I am going to, we'll do one more and then we'll cut it in two here. We have a pretty ugly looking one, which is the integral of ln x dx. What I'm going to do is immediately I'm going to look at, what if I make, and I want to do the wrong substitution at least once. X is inside the natural logarithm. So what if I make u equal to x? Now, a lot of students will try to make this substitution, but this substitution is ultimately pointless because if I make u equal to x, then du is equal to dx. So I could say that the integral of ln x over x times dx is equal to the integral of ln u over u du. Have I really changed anything? No, right? That's really the exact same integral, except now I'm drawing a u instead of drawing an x. And I want to reemphasize that that is okay. If you get it wrong, don't even erase it. Leave it there. Because at least if you can't get the question, I see that you understand it's a substitution question, and I will certainly give you part marks for trying, as opposed to leaving the question blank. All right, so we tried u is equal to x. Let's try something else. Let's make u equal to ln x instead. So if I make u equal to the natural log of x, then du is equal to the derivative of ln x is 1 over x, and then we're going to include that dx piece. Now we're in business because that integral, I'm going to rewrite it just a little bit. I'm going to say that this could be written as the integral of ln x times 1 over x times dx. Those are the same thing, right? Multiplying those fractions across. The advantage of that is through our substitution, I can say that this now can be written as the integral ln x gets replaced by u, 1 over x dx gets replaced by du. You are not going to find much of an easier integral than the integral of u du. So now we can use our integration for this. This becomes u to the power of 2 times 1/2 plus a constant, but u is equal to ln x. So when we make that substitution, I'm going to write the whole thing out, that the integral of ln x over x dx can be written as 1/2 times the natural log of x squared plus some constant. Again, I would highly encourage you, let's check it. It's going to take 2 seconds here before we do part 2. If I want to make sure that this is done correctly, then what I could say is that ln x over x dx is equal to d over dx of 1/2 times ln x squared plus a constant. When I apply that derivative onto the right-hand side, what I get is the 1/2 is out front. The original exponent 2 is there. I'm multiplying by the original function to 1 less, and then I'm multiplying by the derivative of that inner function, and I'll include that dx there. 1/2 times 2 is 1, and I get ln x over x dx. So that shows that we have done our indefinite integral correctly. Okay, we're going to move on. We're going to try, I think there's 3 more, and then of course there's lots of practice for you to do.